Okay, so in the last two videos, we talked about second order homogeneous linear differential equations with constant coefficients in the case where the characteristic equation had two real and distinct roots. But it can happen that the discriminant of the characteristic equation is zero, in which case you get what are called repeated roots. And the question is, what do we do in that case? So first, let's just go ahead and look at a situation where this can happen. So for example, what if your differential equation was something like y double prime plus 4y prime plus 4 equals 0. Okay. Oh, 4y. My bad. My bad. 4y. So this is a second order homogeneous linear differential equation with constant coefficients. Okay. What's the characteristic equation? It is r squared plus 4r plus 4 equals 0. And now the point about this guy here is that if you compute its discriminant, b squared minus 4ac, right? B squared is 16 minus 4 times a, 1, times c, 4. You get 0. Another way of seeing that is that, in fact, this is a perfect square. You can factor this as r plus 2 squared. In which case you see that there is a solution. Take the square root of both sides, you get that r plus 2 must be 0. So r must be negative 2. But this is kind of a repeated root in the sense that, and this is going to be very important later in life, in the sense that this root kind of appears twice in some sense, right? It kind of appears twice. It's, the situation, and I don't know, it's interesting to me that, anyway, so, in the case where we have two real and distinct roots, we might have a parabola, if we graph the quadratic, that looks like this. We get two places where the parabola intersects the x-axis. But what can happen is that in rare situations is that the parabola comes and just kisses the x-axis at a single point. And if you think about it in terms of like an animation, if you think about how if we take a parabola like this and we move it vertically up and down in the plane, we see that there is this there are lots of moments like down here, like the parabola is down here, we see two real roots, yeah? But as you slowly animate this thing going upward, at some point those two real roots, they get married. They coincide with one another in a single root. This is sometimes called there's like a critical threshold happening there where this repeated real root is given birth to, is created from these two real and distinct roots. And as we keep translating the parabola even higher, we see that the parabola completely misses the x-axis. So these repeated real roots are they're at the boundary between having roots and not having any roots over the real numbers at all. Not having real roots over the real numbers, like for example, if your parabola were to look something like this, where it completely misses the x-axis, that's going to correspond to the complex root situation that I was describing in my three cases 2 videos ago. Okay, but that's all. That's important. I'm glad I said it out loud, but how do we kill this problem is the question. So here's the idea. It turns out that in this case, y1 equals e to the negative 2x is a solution. But of course, even though, so because negative 2 is a repeated root, and before we were using those two roots, the two distinct real roots, like in the previous video, to construct a pair of linearly independent solutions, we can't write that y2, which is e to the negative 2x, is a solution, because that's not interesting. y2 is already y1, as written at least, okay? So what do? We put an x in front. And it turns out that in this special case, this is a solution also. Now, you should believe me, but I'll show you this. So y. Y. Well, what's y2 prime? Y2 prime is, now I have to do work. This is another one of those moments where I'm old. I know it's going to work, okay? I'm old, and so I just don't want to. I'm like past the point in my life where like I need to do this for myself. But anyway, I'll do it for you because you're young and you can handle this. And some people even enjoy this kind of calculation. So we're going to do it. We're going to use the product rule, okay? Take the derivative of the first piece, we get 1, and we get, for the second piece, left alone is negative e to the negative 2x. And then we're going to have minus 2x e to the negative 2x. Does that sound right? I don't know. And then we have y2 double prime. Oh, God, I have to take another derivative. So that's negative 2 e to the negative 2x for that one. For the first term. For the second term, I need to use... I have to use... Oh, I should have done it differently. Anyway, I have to use the product rule. So I take the derivative of the first piece, which is negative 2, leave the second piece alone. I add to that the first piece left alone. The first piece left alone, which is negative 2x, times the derivative of the second piece, which gives me a plus 4x e to the negative 2x. Okay? Now we can plunge all this information about y2 into my differential equation, and I should get 0. So if I do that, do I do that? Maybe I let you do that. You should check. You're young. So you should check that when you replace y double prime by y2 prime, let me go here, replace this with this, replace y prime here with this, and replace y here by that you end up getting 0. I'm confident that you will. And I'm so confident that I don't feel like I want to do it. Yeah, that's good. Okay. So indeed, these two things here are solutions, which mean, and by the way, these are linearly independent. You can check that too. That is this, remember what that means. All that means is one is not a constant multiple of the other. Highly plausible, right? This x should really make it clear that these can't be constant multiples of one another. Okay, now if you believe all of that, which you should because it's true, then you learn that y is equal to e to the negative 2x plus the c1 in front. God. Okay, let me do it again. Y equals c1 e to the negative 2x plus c2x e to the negative 2x is the general solution. And this follows, again, from the theory that we established for linear second-order differential equations. If you have a pair of solutions to a linear second-order differential equation, regardless of whether it's got constant coefficients or not, and it's homogeneous, then by the superposition principle, these linear combinations here of this form are again solutions. And by the existence and uniqueness theorem, this is the complete set of solutions. Every solution looks like this. Okay? Okay, great. So that's our situation in this case. Why does this x here kind of make an appearance, right? Because this technique is always going to work. Maybe I'll frame this as a general statement. So, if let me say it like this: given the equation y double prime plus py prime plus qy equals 0 has a repeated root in the characteristic equation, r squared plus pr plus q equals 0, the general solution a repeated root, and let's can I give a name to the repeated root? Can I call it r, please? I don't know why I'm asking your permission. Then the general solution is y equals c1 times e to the rx. That's totally in line. Plus c2 times x e to the rx. Okay? This always works, in other words, in this case, with this remedy of putting the x out front. Why does this x thing, putting it out front, and I will end the video this way, why does it work? And maybe this is even optional, but for those that want to know, the basic idea is that, well, let's say that you had two real and distinct roots, r1 and r2. Then if you took e to the r1x minus e to the r2x, and you divided this by r1 minus r2. If when r1 and r2 are real and distinct, this is a solution. You agree with me? This is a linear combination of the two solutions when r1 and r2 are real and distinct. But now take a limit as r1 gets closer and closer to r2. And observe that this is like the derivative. If you take a limit as r1 goes to r2. This is a derivative. And this is like ddr of e to the rx. It's weird. We're taking a derivative with respect to r. And when we I should say of r1x, maybe ddr1, let's say. In which case, the derivative of this by the chain rule, the derivative of r1x with respect to r1 is x. So we get x e to the r1x. That's how that x makes an appearance. Does that make any sense at all? Makes sense to me. That's maybe one way of justifying it. Here's another way of justifying it, though. It works. You can check it, young brains. With your young brain, you can just go ahead and check it. And so I highly suggest that you do that. Okay? It just works. And you can check it, of course, that it's linearly independent, not a scalar multiple of the other solution. And so you win, win, win. Okay. That's enough for this. See ya.